All right, so we've made it to almost the end of all the mechanics in this class. So we're going to go from mechanics, we're going to finish that up, then we're going to move on to, I think like atomic physics is next. So if you've enjoyed this mechanics section, I would imagine the exercise science folks in the class has probably enjoyed this because it's so applicable. You'll be sad, I guess, because we're getting ready to move to something else. But if you hated mechanics, then you're in luck because we're going to move on to some things that are completely different. Um, but I will say, in this topic, in this module, we're going to talk about something that was very pivotal for me when I was an undergrad, because I wasn't originally a physics major. There's one particular topic in this module and one particular demo that I saw that made me instantly change my major to physics. So I hope you get as much enjoyment and wonder out of it as I did. But before we get there, we have some preliminary things to talk about in terms of uh, this new module, which is rotational motion. So you can think back to when we were talking about things just moving in straight line paths. Um, we're going to use a lot of the same ideas, but it's going to actually be in a circular path instead of a straight path. All right. Like before, we talked about linear speed, which sometimes we just call speed. Um, and this is simply just the distance traveled per unit of time. So the speed would be distance over time, right? Nothing to it. We all remember that. Um, we can also think about the linear speed of something moving along a circular path. Um, we can essentially call that the tangential speed. And this is because the direction of motion is tangent. Remember, tangent would be like a line that just barely touches something, just at one point. So this would be like a tangent line. Um, so that would be our tangent there. So the whole idea is just linear speed moving along a circular path. Since it's sort of grazing the edge of the circle, it's just called a tangential speed. The direction of motion, right? So the where it's going is just tangent to the circumference of the circle. So for circular motion, we can use the term linear speed and tangential speed interchangeably. And just like always, the units of linear or tangential speed is meters per second, kilometers per hour. And you'll see that over here on this image, we'll talk about on the next slide, the tangential velocity is essentially what's going on here. So the whole idea is essentially if some object here, we'll call this object one, travels this distance here on this green arrow, well, they do go over some distance, right? Per time. So we'll call this d over t. Same thing over here. Some object goes through this smaller distance also for some amount of time. So this would also be some distance over time. And now, if you think about it, both of these objects, object one and object two, they both go through the same angle in the same amount of time, right? So the t's here, the time taken to go across these two paths is the same, but this one went over a larger distance. You see how this arrow, this path is longer than the other one? So clearly, tangential velocities depend on where you're at on the thing that's rotating. The further out you are, the higher or larger your tangential velocity is going to be. The next thing to think about would be rotational speed. Now, we've done the whole distance over time thing forever, but Something else to think about is we can also talk about the number of rotations or revolutions per unit time. So you've talked about like RPMs when something's spinning, like your engine or a drill or something. Um, Everything on this disk over here, uh, everything on here is going to spin at the same time. There's no piece of the disk that's going faster than the other. Um, so the whole idea is that the revolutions per unit time stays the same. So essentially, both of these particles, particle one and particle two, we're going to sweep out the same angle. And I've labeled it there with theta, but I'll do it bigger. So they're both going to sweep out that same angle at the same time. So we can reiterate this. Um, so consider two objects sitting on the turntable. Okay, so I've labeled it here. Well, that's going to bug me. It should be plural. Two objects sitting on a rotating turntable. Which of the two objects has the larger rotational speed, and which of the two objects has the larger tangential speed? All right, well, we talked about the rotational speed already. That was the second thing we talked about. That's the angle. Okay, so the rotational speed, that's all about how we're going through some angle over some time. Now, remember, we said that both object one and object two, if you look at the pink here, they're both going through the same angle in the same amount of time. So that means both objects one and two have the same rotational speed. Okay, since they both sweep out the same angle at the same time. So that means omega, which is how we're going to measure the speed. Omega is simply just how your angle's changing over time. Yeah. Okay. Now, the other question is the tangential speed. So object one, in this same amount of time, right? In everything we're talking about here, everything spinning the same amount of time. In the same amount of time that object one covers this long distance, called big D, in that same amount of time, object two covers the smaller distance. We'll call it little d. So the whole idea here is that the velocity of the first one, since the velocity is just distance covered over time, well, there's way more distance here, right? Big D, longer distance. Okay, there's way more distance there covered than the second object. Because that second object, it just had this little distance. Not a lot's covered. So that means velocity, I put everything in capital letters to reiterate that it's bigger distance over time. So this velocity is going to be larger. Our second velocity, velocity two, isn't going to be as big. So the velocity of the first object is going to be greater than the velocity of the second object. That's because it's further away from the radius. Further away from the radius. No, that doesn't make any sense. Its radius is larger because it's further away. Oh, great, and my eraser's not working. That's okay. So it's further away from the center. That's what I want to say. All right. That's going to bring us to this point here. We say that the tangential speed, which I'm going to write as VT, remember that's the whole idea of the circular path. And then at any given instance, we've got this tangential velocity or tangential speed. Although we're turning at any one instance, it kind of looks like we're pointing off on this tangent path. So the tangential speed here is actually directly proportional to the rotational speed. So that makes sense. There's how fast we're going around the circle does depend in some way on how fast we're sweeping the angle out. Remember, that's the change in the angle over time. The tangential speed also depends on the radial distance. And we just talked about that on the previous slide. So this is the distance from the axis of rotation. So essentially your radius. So VT depends on two different things here. Since it does depend on both, we can actually essentially write out this statement that the tangential speed is proportional to the radial distance, r, times the rotational speed, omega. Now, if we look at this example over here, we have these two little ladybugs. And first we could talk about the radial distance. Okay, so this first one has a radial distance of whatever you want to call this, halfway across the turntable. The second ladybug has double that, which means even though this ladybug is going fast, if you increase, notice the equation here. If you increase r, the radius, your tangential velocity also has to increase. So even though this first ladybug is going fast, if you double the radius to r, you're going to go twice as fast. But remember, they have the same omega. The angle that this is changing is the same. What's making the outside ladybug go faster is because it's further away. So if we think about the angle being swept out here, the angle theta, that's going to be the same for both ladybugs. Why did we write out the tangential speed as a proportion and not just straight up equal signs? And this is important. So right now, if you think about what we just did, we said that the tangential velocity is proportional to the radius, or how far away an object is from its axis of rotation. And it's also proportional to its angular velocity, so how fast it's sweeping out the angle. We measured those, the distance from the center, we usually measure that in meters. And then we've been talking about the omega, or the angle swept out, or how many revolutions. We've been talking about that in, you could say angle over time, or the previous slide we said RPMs. So that's going to be some really dumb units, right? Right now, our units are meters times RPM. They don't really match up, or these don't really mean anything. Yeah, so the question is, what is a meter revolution per minute? Because that's literally what our units are right now. That doesn't make any sense. So if we want to be like pinky out proper, we can discuss omega in terms of radians per second. You know, this is getting closer to the whole change in theta over time, because you can measure the angle in radians, you can measure it in degrees, but we don't need to do that right now. We'll deal with that later. So the whole idea is that we can actually measure omega in radians per second. And of course, there's 2 pi radians in one full circle, just as a quick reminder. And then since all this motion that we're talking about is circular, we can think of omega as just having units of essentially 1 revolution per second. And if we just say like, well, it's always going to be on the circle, we can ignore the whole 1 revolution part and just say, well, it's inverse seconds, 1 over seconds. So if we decide to really run with this and try to be proper, then we'd have our radius, still measured in meters, times our fancy units, inverse seconds, or just 1 over seconds, because we're talking about revolutions in radians per second. Now look at what happens. We can multiply these two things. Well, the meters just goes into the numerator, and that gives us what we would expect, meters per second. Okay, now these are the proper units of velocity. If we measure with radians per second or just inverse second, then we get to write the equal sign, okay? So that's why for now, since we have these really weird units, we're just using the proportion and not the equal sign. So just like we talked about before, anytime when a speed undergoes a change, it's due to an acceleration. So the idea here is essentially acceleration is the old final minus initial over some time, t final minus t initial. Now the whole idea here is that when a tangential speed, right? So instead of just a straight line speed, now we're going to talk about a circular speed. When a tangential speed undergoes change, we speak of a tangential acceleration. Literally all that means so we're talking about the final minus initial tangential acceleration over some change in time. Any change in tangential speed indicates that there's an acceleration that's parallel to the tangential motion. So if we're going to speed up, and remember we've got this tangential speed, tangential direction going on, all this is saying is that we either have an acceleration to speed us up around the circle or an acceleration to slow us down around the circle. Either way, it's going to be parallel with the direction that we're moving. For an example, you could consider a turntable like we've been talking about, starting up from rest, because that's going to be no movement, zero initial tangential velocity, and then it's going to get up to some speed. Or we could go the other way. Maybe we're talking about like merry-go-round that's moving and then it's slowing to a stop. So those are really basic examples of just tangential accelerations. There is one other kind of acceleration. So we're talking about how things are moving on the edge of these paths. But remember that these things are all anything moving in a circular path. Anything moving in a circular path is always changing its direction. It always has to turn into the circle or into the circular path. It never travels in a straight line. As soon as it travels in a straight line for any distance, you don't have a circle anymore. You don't have a circular path. So Newton's laws tells us that for something to change its speed or direction, a force must be acting. That means there's got to be some force causing us to keep changing our direction continuously. So what could that force be that's causing us to always turn into the circular path? This is where we get to centripetal force. So any object moving in a curved path undergoes an acceleration that points toward the center of the circle. This is the centripetal acceleration. So even if you're driving in your car, maybe you go over a hill and you hit a valley, you go over a hill, you hit a valley. Even in your car, here's the center. As you drive through this dip in the road, as you drive through this dip, the road is holding you in a circular path. So your acceleration is always going to point toward the center of this invisible mathematical point that's the center of this circular path. right? So here's essentially your axis of rotation, or your point of rotation, I guess you could say. So even just driving through a dip in the road, you're going to have some sort of centripetal acceleration that's pointing toward this fictitious central point in the circle. Centripetal literally just means center seeking, or toward the center, right? Toward the center of the circle. Uh, Newton's second law states that if there's an acceleration, we have an acceleration pointing into the center of the circle. Well, if an acceleration is there, then a force must be there. So what is the centripetal force holding us in circular motion, right? We know something has to hold us in there because our direction's changing. We're accelerating toward the center of the circle. So something's holding us in circular motion. What could it be? Well, it turns out this is a bit of a trick question. So the centripetal force is not actually its own like force found in nature. It's essentially the name given to any force that's going to hold us inside of a circle. So gravity holds the moon in a circular orbit around Earth. So this is Earth. Here's the moon. In this case, we have our action-reaction pair. Gravity is our centripetal force. Electrical forces, or electrical force holds electrons in orbit around a nucleus. So if we have a nucleus, we have all these electrons zipping around it. The electrical force is our centripetal force. Now moving to examples that we can see more in our everyday lives. If you look at this car up here, it's turning left into the circle. Well, friction from the tires, that's what's holding it in the circular path, right? You turn your wheel, tires are digging into the ground. So this centripetal force, it's not its own thing. This is actually from friction. Tension, holding an object on a string as it's spun around. You can see here, you know that there's a tension force, because that's what's always pulling in on that object as this girl spins it around her head. So in this situation, the tension force is actually our centripetal force. So anything that moves in a circular path does so because it's acted on by a centripetal force. The centripetal force can be anything. It's whatever's going to be holding that thing in a circle. It turns out that the centripetal force depends on the mass of the object going through the circle, or the circular path. It also depends on the tangential speed, which makes sense. If the thing going through the circular path is really far away from its central point of that path, then you're probably going to have a big centripetal force that's going to hold it there in the path. So that's why it not only depends on how fast it's trying to go through the circular path, it also depends on the radius of curvature. And that really is just the radius of the circular path it's traveling. So we've got three things here. We can put them all together, and essentially the relationship between these variables is this. So our centripetal force is essentially mv squared over r. Notice that the speed is squared. So if we want to double the speed, we need 4 times the force. So times 2 for speed would be 4 times the force. The inverse relationship between radius tells us that if we cut the radius in half, well, if we cut the radius in half, you can think about it. If you start spinning something around your head and then you make the string shorter, it speeds up and you can feel it. You can feel the tension increase. So if you decrease your radius and start making that spin faster and tighter, then you're going to need more force. to hold it in the circle. So 1/2 the radius is going to be double the force times 2. Now, if the centripetal force suddenly just disappears, remember the centripetal force is anything holding an object in a circular path. If that centripetal force suddenly just goes away, the object will no longer have any forces acting on it. Now, let's just ignore gravity for a minute, right? And just for just that moment, as soon as something happens, so here, our tension force suddenly goes away, it snaps. As soon as that force is removed, Newton's first law takes over. And hopefully you remember Newton's first law that says when all the net forces add up to 0, well, we have no forces, so it's going to be 0. An object in motion will stay in motion, traveling in a straight line. You remember that from Newton's first law. Anything that's already moving will continue moving at the same speed and same direction. Same speed, same direction. So that means as soon as this string breaks, this object's going to just take off, just hauling in a perfectly straight direction, and it's going to be tangential to the circular path. So as soon as you lose your centripetal force, whatever object you have, straight line from there on. And it is on a tangent path. And this is exactly how a washing machine works during its spin cycle. So the clothes, it's spinning, the clothes are pressed up against the wall of the drum. Well, okay, so the clothes are pressed up against the wall. Newton's third law says there's got to be a reaction. So the wall is going to push back with the normal force, right? So you can see, if we look inside this drum, you're going to have a normal force pushing in. The normal force is going to hold all the clothes inside. That's your centripetal force. Remember, the centripetal force has to be caused by something. So here it's caused by the normal force. But since there's all these little holes, these pinholes, it's almost like a mesh inside your washing machine. The water droplets, they pass through the small holes in essentially a straight path, a tangent line. You can see here, these are coming out all sort of in straight lines that are tangent to the circular motion. Now let's use this definition of centripetal force and actually do a calculation here. So what is the tension in a horizontal string that whirls a 2-kilogram toy in a circle of radius 1.5 when it moves at 2 meters per second? That's a lot of information, so we should start with the picture, which we have over here on the right. Okay, so it's asking what is the tension. So we know we're looking for T. We know that the toy that's spinning in the circle is 2 kilograms. So we know the mass. We know the radius of the circle. The radius is 1.5 meters. And we know the velocity. And what color haven't I used? Blue. Okay. And we know the velocity, which is just 2 meters per second. Okay. So the tension is supplying the centripetal force. So we could literally just write T equals, right? Same thing. Well, we use our centripetal force calculation here. So we have mass times velocity squared divided by r. We know all these values, so it's simply just a plug and chug. And it turns out the tension in this string is 5.3 newtons. All right. The next thing you probably heard about is centrifugal force. So it looks like centripetal, but notice it's centrifugal, or some, I've heard it called centrifugal forces, which is weird to me. So for me, it's centrifugal. So although we do have the centripetal force, which is center directed, right? So an occupant inside a revolving or rotating system. Um, right. Okay. So we do have this inward force, which is centripetal. But if we're riding along, like maybe in a car, and the car decides to turn right really quick, or the driver just yeets around a curve, um, if we're inside the car, it feels like something is slinging us out, right? We're sort of pressed up against the door. So this is an apparent, and that's important. This is an apparent outward force, and that is our centrifugal force. And shocker, centrifugal just means center fleeing or away from the center. So it turns out the centrifugal force isn't actually, it's not a real force. It's not caused by a real force. It's actually just an element of inertia. You're trying to go on that same path you've been traveling. The car decides to turn really quick. So the car starts circular motion, but you want to go in a straight line. So that's what you're feeling is you trying to keep going straight. The car takes off before you do to the side, and that's why you get smacked up against the door. You don't get thrown into the door comes to you. But you don't always see that. When you're riding along in the car, it feels like something's pushing you up against the door, but that's not the case. Uh, so the centrifugal force feels like gravity, but there's no action reaction pair. Remember, for Newton's laws to work, there has to be an action and equal and opposite reaction between two objects. There's no two objects, nothing produces the pulling for a centrifugal force. So for this reason, physicists call it an inertial force or a fictitious force. But nonetheless, observers who are in the rotating system or the turning system, like if you're riding in the car, the centrifugal force feels like a very real force. Now, if we're standing outside the car watching, we can be like, oh, look, the car door is providing the normal force to hold this person in the curve, right? We can see that happening when we're out watching the whole thing, the whole scenario. But when we're riding along inside, we don't get to see that rotation. We just feel something pushes up against the door. And you can think about that here. If we consider a toroidal rotating space station, the centripetal force from the rotation produces an artificial gravity. So on this whole city and all these towns and the people and the water, you see how it sort of turns up as you go this way. So it turns out what you're looking at is all of that is actually along the wall of this rotating space station. So the idea is that if you spin it at the right speed, you throw everybody and everything up against the wall, and as long as it keeps spinning, people sort of get stuck there up against the wall. So the centripetal force from the rotation produces an arc of gravity. So as the space station spins, people will sort of be stuck to the wall. Now, on the outside looking in, like if we look at this top picture, we know that what's going on is actually the wall is providing a normal force, right? That's the thing, that's the physical piece holding everybody and everything in this circular path. So we know this is actually our centripetal force. But the whole thing with the centrifugal force, it's all about a frame of reference. So if our frame is outside the space station, we can see what's going on. We can see the rotation. We know something is rotating. We know the normal force is causing the centripetal force. You can see that here. This is if we watch outside. Normal force is causing the centripetal force. Now, if we move our frame of reference inside, so suddenly we're in here, if our coordinate system and our frame of reference and our grid is suddenly riding along, that's important. So instead of just having our frame of reference sitting here watching, suddenly our frame of reference is moving, right? So if we are moving with the circular space station, then we don't know that the space station is rotating. It's just like how we're on the Earth rotating. So our frame of reference is rotating, but we don't feel the Earth move. We don't really have anything other than the stars at night to know that the Earth is moving. So really for us, even though we're in a rotating system, we don't really notice it in our day-to-day lives. So the whole idea here is that because this reference frame is suddenly riding along, what happens is everyone inside suddenly feels gravity, and there seems to be some sort of force pushing them down against the wall, but really that's just this fictitious centrifugal force. If we step back outside when our reference frame is not moving anymore, then we know it's actually just the normal force holding them. Just for some applications, so the occupants of today's space vehicles, they feel weightless because there's no support force, right? You need something that's going to spin at just the right speed for this centrifugal gravity to be created. And we don't have space stations nearly big enough, right? So they don't spin, they don't experience a centrifugal force, they're just floating in space. And just for reference, simulating Earth's gravity like this, you'd have to have a very big circular space station with a radius of 1 kilometer. I mean, that's huge. And would have to rotate at 1 rotation per minute. So that's spinning very quickly. And that is a very massive ring to actually build in space. I mean, 1 kilometer. So let's take a look at an example and then we'll call it. So if Earth were to spin faster about its axis, your weight would be less. But if you were rotating in a space habitat and it started spinning faster, you would weigh more. So why do we have these different opposite things going on? So essentially, if the Earth speeds up, you would kind of be like the water in the washing machine example. You would be more likely to be tossed off the planet. So as it's spinning, you would be more likely to be tossed off the planet on a tangential path, right? There's no normal force to hold you in circular motion. However, if you're inside a spinning space-based habitat, then you'll just be pressed against the wall. Oops, you are pressed against the wall. And you would simply just, your normal force would increase, right? So the wall is just going to push back harder and harder. And essentially, you could be like pressed into it until you're goop, but you're not going to leave that circle, right? That normal force, as long as the spaceship holds up, you're going to have that normal force holding you in the curved path. So we'll stop there. And next time we'll talk about a few tidbits: rotational inertia, torque, and center of mass. Then in the third lecture of this module, we will talk about my favorite thing, conservation of angular momentum, and that is the reason that I became a physics major. So we'll get there. But for now, this is just the basics of circular motion.